Dear students, this is our 8th class and this is the last class on the chapter Fourier Transform. And in this class, we will focus on the following topics. Now, first, Fourier Transform of derivatives. Then, Fourier Transform to solve differential equations. For example, solution of partial differential equation and within which one-dimensional heat flow and wave equation will be solved using Fourier Transform. And we will solve a problem relating to these kind of partial differential equation. So this is the topics that we will be discussing in this class. Now let us start. First, Fourier transform of derivatives. If f omega be the Fourier transform of the function fx, you consider that f omega is the Fourier transform of the function fx. And then the Fourier transform of the derivative of fx, that is Fourier transform of df dx, is minus I omega f omega, and this is the value for case of and this kind of problem we have solved a problem like this in our previous case. But in this case, in this discussion, we will prove this in another way. So if f omega is the Fourier transform of the given function fx, then the Fourier transform of the derivative of the function fx that can be given as df, that is the Fourier transform of the function df by dx is I minus I omega d omega. We will here prove this. But in this case, the technique is different from that we employed in our previous problem that has discussed, that has studied in our previous class. So let us prove it. We know that it is not very difficult to understand that we know that the Fourier transform of the function fx is mathematically defined as f omega, that is 1 by root 2 pi, then minus infinity to plus infinity fx e to the I omega is dx. This is equation number 1. And now we consider that the Fourier transform of f prime x, where f prime is nothing but the first order differentiation of the function fx with respect to x. So ft means Fourier transform. So Fourier transform of f prime x, that is equal to Fourier transform of df by dx, and we are taking this as f1 omega, that is equal to, just use this relation. In this relation, this fx could be replaced by df by dx or f prime x. So that is equal to root 2 minus infinity plus infinity f prime x e to the I omega x dx. Now the integrand, that is this part, minus infinity plus infinity f prime x e to the I omega x dx. So the integrand part, that is this term fx f prime x e to the I omega x dx, can be written in this way. You know the definition of differentiation of a function fx around the point h, when h tends to 0, can be written as limit h tends to 0 fx plus h minus fx by h e to the I omega x. You know the definition of differentiation of a function. So this is the definition of the differentiation of the function fx around the point x, where around the point h, which just tends to 0, and then can be written as the value of the function when x is increased to h from the h, that is fx plus h, minus the value of the function x, that is here, divided by h when h tends to 0. And I am just finding out the value of this f prime x to the I omega dx. So you can write this term f prime x to the I omega dx, that is here, and e to the I omega x. That is equal to limit h tends to 0. I am writing this first term as usual, x plus h, and this h is here, and just divide this into two terms. One term relating to f of x plus h by h e to the I omega x. Other part is minus fx into e to the I omega x by h. These are two terms in this expression. So writing the first term here, h tends to 0, limit h tends to 0, fx plus h by h, then e to the power I x plus h into omega. So in this case, what is the extra term? Extra term is omega I omega h. So you can multiply this in this, you can write in this expression e to the minus I omega x. So because you have e to the power I omega x, so it is an e to the power I omega and then x. The extra term is there e to the power I omega h with a positive sign. So you should be multiplied this term as e to the power by e to the minus I omega h. So this is okay. Now minus the next term uh, minus fx by h, that is fx by h e to the I omega x. Okay. So therefore from this relation f1 omega, that is equal to limit h tends to 0, then f omega is the part. Now just substitute these values in this expression. Then you will have 1 by root 2 pi, then minus root 2 plus infinity, limit h tends to 0, x plus h, then by h e to the I x plus h omega, then into e to the minus I omega h, and then another term will be then dx, then another term will be 1 by root 2 pi, then minus root 2 plus infinity fx by h e to the I omega x dx. There should be two terms, and you know that 1 by root 2 pi, 1 by root 2 pi. So here is on the first term, limit h tends to 0 is written here, and in this case when h tends to 0 for the limit for this function, when h tends to 0, that means fx by h, and here e to the power I omega x, and using the Fourier transform of this first from the first term, you will have f omega, and the extra term is e to the I omega h, that is there. So just use h when h tends to 0, because the limit still remains here, because for the term e to the I omega h, for this term only, by h for this term. But if you use h is equal to 0 in this function, then it will provide you fx, and from here e to the I omega x. Okay, and if you use this value in this expression, that will give you f omega, the remaining term with this e to the I omega h, that is here by h. And from the second part, this is the second part, e to the fx to the I omega x dx, and this will give you f omega, and this h is here. So now from here you just take f omega as the common term. F omega is here, limit h tends to 0, from here e to the I omega h, from here minus 1 by h. Okay. Now if you now write or use h is equal to 0 in this expression, then the first term will be plus 1, then minus 1, that will provide you 0, and here 0 by 0, that means it will be undetermined. And in that case, you have to apply L'Hospital's rules. And according to L'Hospital's rules, you have to differentiate the numerator as well as the denominator. Okay. So after that, with respect to obviously this h, so that from that applying L'Hospital's rules, from this expression, you will have f omega, then limit h tends to 0, and this will give you minus I omega e to the I omega h, and this h will give you 1. So you will have the value h tends to 0, minus I omega e to the I omega h. From here, using L'Hospital's rule, that means differentiating the numerator as well as the denominator. So from here, you can write I minus I omega, then f of omega. In this case, you have applied the value h is equal to 0. Just put here h is equal to 0 in this expression. This will provide you I omega f omega. So from here, so f1 omega is equal to minus I omega f omega. This is for the first order differentiation. And in case for the second order differentiation, it would be f2 omega, that is minus I omega. You can write that square, then f omega. In this way, f3 omega, that would be minus I omega to the power 3, then f omega. In this way, fn omega, that is the Fourier transform of the nth order differentiation of f is then I omega to the power n will be here, then f omega. You can prove in this way also. Now, Fourier transform to solve differential equations. In this section, we learn how Fourier transform can be applied to solve differential equations. To illustrate the application of Fourier transform in solving differential equation, we consider the motion of a damped harmonic oscillator. Therefore, we are considering here the motion of a damped harmonic oscillator. You know that in case of damped harmonic oscillator, the forces acting on it is restoring force. Restoring force means that force which brings it to its initial condition, and that is nothing, that is proportional to the displacement negative of the negative of the displacement of the bob of the harmonic bob of the pendulum. Okay, bob of the particle, or the displacement of the particle. That means the restoring force is minus lambda square omega, where lambda is a constant, lambda square x. This is the restoring force. Another force which actually resists it, that is resist its movement, which is proportional to its velocity, that is dx by dt, and that can be written as 2k, that is the constant dx by dt, and this is the acceleration of the of the particle. So the equation of motion can be written in this way: d2x by dt square plus 2k dx by dt, then plus lambda square x, that is ft, where ft is the periodic force that is applied on the particle. Okay, so now just we know that, or we can write ft. This is ft, that is equal to, that can be written as, that is the inverse Fourier transform of its Fourier transform. So now let's just go for the first, go for this case. First, for this, f omega is the Fourier transform of ft, that is equal to 1 by 2 pi minus 20 plus ft e to the I omega t dt. It is okay. Now the Fourier transform, inverse Fourier transform of f omega, that is ft, that is here, is equal to 1 by root 2 pi minus 20 plus infinity. This omega is here, then e to the minus I omega t into d omega. This is the inverse Fourier transform of this omega. That means ft. So f omega and ft are the Fourier and inverse Fourier transforms. We know it all. Now taking the Fourier transform of both sides of equation 1, that is our equation is here, and we are taking now the Fourier transform for both sides of this equation. That means 1 by root 2 pi, then minus infinity to plus infinity, then this d2x by t square e to the power I omega t dt. This is the Fourier transform of the first term, this term, plus 2k by root 2 pi minus infinity plus infinity, then dx by dt e to the omega t dt, plus lambda square by 2 pi minus infinity to plus infinity, and then xt e to the omega t dt. That is equal to, for this 1 by root 2 pi, it is root 2 pi minus infinity plus infinity ft e to the omega t dt. So taking Fourier transform for both sides. Now you know that this is nothing but the Fourier transform of the second order differentiation of the function x with respect to, and that will provide you minus I omega whole square, that means minus I square omega square, and then x of omega, where x omega is the Fourier transform of the function x, that is here. Okay, and then this 2k is here, 2k by root 2 pi will be here, 2k, no, sorry, this is the definition. So this 2k is here, and 1 by 2 pi minus infinity plus infinity dx by dt to the omega dt, that is nothing but the Fourier transform of the first order differentiation of the function x, that is minus I omega, that is here, minus I omega, then this 2k is here, and x omega is the Fourier transform of the function x, so that is here. After that, lambda square is here, and this is the Fourier transform of the function x, that is x omega, that is equal to f omega. What is f omega? It has already defined. F omega is the Fourier transform of the function f. So that is here. So that all everything x omega. What is the x omega, or the definition of x omega is also here written here, and the condition is also written here. So from this relation, this will provide you minus omega square x omega minus 2k I omega x omega plus lambda square x omega, that is equal to f omega. And from here you can write x omega, that is equal to f omega by minus omega square, then minus 2k I omega plus lambda square. So this is this will provide you the value of the Fourier transform of the function x, that is x omega. And now if you take the inverse Fourier transform of this term, then that will provide you the function xt. So Taking inverse Fourier transform of this function, that is x omega, we get the function xt, that is equal to 1 by root 2 pi minus infinity plus infinity x omega e to the minus I omega t d omega. Okay. Now just substitute the value of x omega here in this expression, xt, that is equal to 1 by root 2 pi minus infinity plus infinity, then f omega by lambda square minus omega square minus 2k I omega, then e to the minus I omega t d omega. So now from the knowledge of f omega, you can comfortably calculate the value of xt, that means the solution of this differential equation, the solution for x for this damped harmonic oscillator, for the equation of damped harmonic oscillator. Okay. Now, solution of partial differential equations, boundary value problems. In this case, we will learn how to solve boundary value problems using Fourier transform. So, partial differential equation can also be solved by using Fourier transform, and that can be illustrated. That is illustrated in the following examples. First one is one-dimensional heat flow. You are very familiar with the one-dimensional heat flow equation, that del U, that is a function of xt, U is the temperature function, and del T, that is h square del T U, a function of xt by del x square. When x greater than 0, t greater than 0. You are very well known, you know the one-dimensional heat flow. The equation is here. H is a constant. So where xt is the temperature function. Okay. Now let us we impose some boundary conditions on this heat equation. Number one is both of uxt, that is uxt, and del u del x, that is the differentiation of u with respect to x, tends to zero when x tends to plus minus infinity. That means when the distance is very higher, very large. In that case, both the temperature as well as its gradient with respect to a distance both vanishes. That means x tends to 0 when x tends to plus minus infinity, then uxt as well as del u del x both vanish. Okay, this is one of the initial condition. And another initial condition that is imposing on this problem is uxt, that is equal to when t is equal to 0, then this is exclusively a function of x. Okay, it is very clear from this expression that uxt when t is equal to 0, then uxt is exclusively a function of x, and that is fx. We are taking. So two conditions are here. Number one condition is, the first boundary condition is when x tends to plus minus infinity, then uxt as well as del u del x both becomes 0. And the number two is when t is equal to 0, uxt, that is equal to ux0, that is a function of x only. Now we define Fourier transform of uxt, that is the function, that is the temperature function uxt is here, and its Fourier transform can be defined as u omega t, that is 1 by root 2 pi minus infinity plus infinity, u, the function is there, uxt, then e to the I omega x dx. Okay, this is the Fourier transform of uxt. We are considering, or we are taking this definition that the Fourier transform of the function uxt as given as u omega t, that is 1 by root 2 pi minus infinity plus infinity uxt e to the I omega x dx. This is equation number 3. Now taking Fourier transform on both sides of equation 1, that is, where is the equation 1? This is our equation 1. Now taking Fourier transform on the both sides of this equation, that means 1 by root 2 pi integration. So that is here 1 by root 2 pi integration minus infinity plus infinity del u del t. The first term is del u del t, you see here del u del t, then e to the power I omega x dx, that is equal to 1 by root 2 pi. After that, this h square see here, this h square is here, and integration minus infinity plus infinity, that is here del 2 u by del x square e to the power I omega x dx. Just taking the Fourier transform on the both sides of equation number 1. So that from this, you see from here that you can write this in this way, that this del t or ddt can be taken outside the integration sign. So in that case, d dt of 1 by root 2 pi del 2 pi, then u e to the I omega x dx. That will provide you the Fourier transform of u, that is u of omega t. And from here you can write, see here, this is the Fourier transform of the function u, Fourier transform of the second order derivative of u with respect to x. And you know, already you have known that the Fourier transform of this term will give you minus I omega square, that is I omega square, and then I omega square, and then u of omega t. You know, for the second order derivative, minus I omega whole square, then u of omega. So that is here. So minus I omega square means that will give you I square means minus 1. So h square omega square u ut, u of omega t. Just use the, you already know, you have known, you have the knowledge of this dimension. That is second order differentiation of x, Fourier transform of second order differentiation of x, sorry, u with respect to x. So this is here. Now just write this as integration. Now from this relation you can write this del omega du of omega t by this u of omega t, that is into minus h square omega square dt, integrating both sides. That is here ln log omega ut from here, that is into minus h square omega square t plus log a is a constant. And from here you can write u omega t, log of u omega t, and this log a after taking here. So log u of omega t by a, that is equal to minus h square omega square t, or u of omega t is equal to a e to the power minus h square omega square t. This is equation number 4. Okay, we already now we have completed, we have calculated the value of u omega t. Now from equation 3, using, now where is equation 3? It is your equation 3, and in this equation you write t is equal to 0. So writing t is equal to 0 in equation number 3, we have here u of omega 0, that is omega 0, that is 1 by root 2 pi, that is here 1 by root 2 pi minus infinity plus infinity, u of x, and then 0 e to the power I omega x, and then dx. That is equal to 1 by root 2 pi. You know, this is the boundary condition number 2, that is in case of t equal to 0, u xt, that is equal to u x of 0, that is equal to a function of x only, that is fx. It has been already stated in case of second boundary condition. So 1 by root 2 pi minus infinity plus infinity fx e to the I omega x dx. And what is that? This is the Fourier transform of the function fx, that is the omega. So u of omega 0, that is equal to f omega. This is equation number 5. Taking from equation 4, this is equation number 4. Writing t equal to 0 in this equation. So from here u of omega 0, that is here, that is equal to a e to the power 0 means e to the power 0 means 1. So a, only a. And also you have seen that in case of this, in this case, u of omega 0, that is equal to f omega. So this a is equal to f omega. From these two equations you can write a omega. So therefore from equation number 4 we can write u of omega t, that is equal to this a is equal to f omega, that is f omega, then e to the power minus h square omega square t, that is here. So we in this case we calculated the value of u omega t, that is this. Now we need to have the knowledge of the u xt. So in that case you have to you have to use the inverse Fourier transform. So the inverse Fourier transform of this u omega t, that is nothing but u xt, that is equal to 1 by root 2 pi minus infinity plus infinity, then u of omega t e to the minus I omega x d omega. This is the definition. So that is equal to 1 by root 2 pi minus infinity plus infinity, then f omega, writing the value or substituting the value of u omega t, that is this f omega, then e to the power minus h square omega square t is here, and after that e to the minus I omega x is there, then d omega. Now let us consider that this value e to the minus h square omega square t is equal to g omega. Just taking this value as this. So u x t is equal to 1 by root 2 pi minus infinity plus infinity f omega g omega e to the power minus I omega x d omega. So this is the solution for for uxt. So this is the solution of one-dimensional heat flow, and the temperature function can be find out in this way using Fourier transform. So now going to the next problem. This is another example. Another example to solve wave equation. So in case of wave equation, consider the vibration of a very long infinite elastic string fixed at both ends. The string is fixed at both ends. The one-dimensional wave equation is given by, you are very familiar or you have learned about this type of equations in wave and acoustics in the graduation level. So I am writing directly this equation. So del 2y by del t square, that is c square del 2y by del x square. This is the one-dimensional wave equation for a string which is flapped at 2x. So where yxt is the displacement of the string at any time t, and such that yxt tends to 0 and the del y by del t tends to 0 when x tends to plus minus infinity. That means when x is equal to plus minus infinity, then the displacement dy should vanishes as well as its dimension with respect to t. So when x tends to plus minus infinity, then yxt as well as del y del t is equal to 0, tends to 0. This is one condition. Another condition is here, and the initial condition, another initial condition is here. When t is equal to 0, then y is equal to x 0, that is exclusively a function of x. So in that case, y of x0, that is fx, and del y del t, so it is independent of t. Then in this case y is independent of t, so del y del t at t is equal to 0 should also is equal to 0. So the boundary conditions are here. When x is equal to plus minus infinity, then yxt tends to 0 and del y del t also tends to 0, and when t is equal to 0, then yx0, that is equal to fx, and del y del t at t equal to 0 is equal to 0. These are the two boundary conditions. Now we define the Fourier transform of y, of the function y. You can define in this way, that f omega t, that is 1 by root 2 pi minus infinity plus infinity yxt e to the I omega xt. This is the definition, you know it. There is nothing to discuss about this definition. Now taking Fourier transform on both sides of equation 1, that is our given equation, that is this equation, then 1 by root 2 pi integration minus infinity plus infinity del 2y by del t square to the I omega t, and then dt. So that is here, that is here, that is here, this is here. So 1 by root 2 pi minus infinity plus infinity del 2y xt by del t square e to the power minus I omega xt, taking with respect to x, and that is equal to 1 by 2 pi c square minus infinity plus infinity del 2y by del x square e to the power minus I omega x dx. So this is after taking the Fourier transform both sides of equation. This is equation 1. Then we have this. That is equal to, now del 2 by del t. This can be written in this way, del 2 by del t square. Then 1 by 2 pi minus infinity plus infinity y of xt, that is here e to the I omega xt. That is equal to c square is here 1 by root 2 pi minus infinity plus infinity del 2y by del x square e to the power I omega xt. So from here you can write d2 by dt square, and this is nothing but the Fourier transform of yxt, that is f omega t. So d2 by dt square f omega t, that is equal to c square is here, and this term is the Fourier transform of the second order derivative of y with respect to x, and that value will be minus I omega whole square then f omega t. So that is equal to minus c square omega square. So I omega square means minus omega square. So c square minus c square omega square f omega t. So from here you can write d2 by dt square f omega t, and this is taken in the left hand side. So c square omega square f omega t, that is equal to 0. And this kind of you are very expert to solve this kind of equation. You know the solution of this equation would be f omega t, that is equal to a1 e to the I omega ct plus a2 e to the minus I omega ct. Because in this case you know that in that case we have to use suppose this f omega t is equal to e to the power m omega t as an auxiliary equation, and using that we will have two values of e to the mt. So in this case m will have two values. One is uh, plus omega c, another is minus omega c. So therefore the solution would be f omega t is equal to a1 e to the power I omega ct plus a2 e to the minus I omega ct. So the constants in this case a1 and a2 are two arbitrary constants, and these two constants can be calculated by using the initial conditions. So from the condition y x0 t x0, so from the second condition that was written here, see here, the second condition is y x0, that is fx, and in this case del y del t is equal to 0. So now we are employing, or you are utilizing this condition, that is y x0. In that case it is so y is exclusively function of x, that is fx. Using this we can have the value f of omega 0 from this relation, f of omega 0, that is 1 by root 2 pi. You can write this from this relation. Go to this one, f omega 0 from equation number 3. You just put t is equal to 0 here. F omega 0, that is 1 by root 2 pi minus plus y, then x 0 e to the I omega x dx, and you know that y x0 is equal to fx. So f omega 0, that is 1 by root 2 pi minus plus infinity y, this will give you fx, then it will I omega x dx, and that will give you that is here 1 by root 2 pi minus plus infinity y of x0 e to the I omega x dx. So that is here 1 by root 2 pi minus plus infinity fx. You know that this value of y of x0 is equal to fx e to the I omega x dx. So from here you have obtained this, and also from equation 4, that is from equation this equation, writing t equal to 0, f omega 0, that is here, see here, this is equation number 4, and from here f omega 0, that is equal to a1, this will give you 1 e to the I 0 e to the 0, and this will e to the minus 0, so a1 plus a2. So f of omega 0 is equal to a1 plus a2, and from this equation f omega 0, and here also f omega 0. So from this equation you can write a1 plus a2, that is 1 by 2 pi minus plus fx e to the I omega x dx. This is equation number 5. Now from the condition, that is del y by del t at t equal to 0, that is equal to 0. This is also, in this case, y becomes only the function, exclusively the function of x on x. Therefore del y del t at t equal to 0 should vanish, that is 0. Then also from the equation, that is written here, that is from this equation, del f by del t, that is 1 by root 2 pi minus plus infinity del y x of 0 by del t at t equal to 0 it is deriving x dx. That is also written here. So del f del t at t equal to 0, that is 1 by root 2 pi minus infinity plus infinity del y x of 0 by del t at t equal to 0 e to the I omega x dx. Since y of x0 t vanishes, del t vanishes at t equal to 0, so this del f del t at t equal to 0 should also be 0. So that is also 0, and also from so we get f of del f del t at t equal to 0 is equal to 0. Okay. Now also from this equation, just differentiate it with respect to t. So del f del t, del f omega t del t, that is equal to from here I omega c a1 e to the I omega c, and from here minus I omega c a2 e to the minus I omega c, and writing t equal to 0. From here you can have the value that is here I omega c into a1 minus a2, that is equal to 0. Just write the value of, just use the value of in this expression, just differentiate this with respect to t and this also, and then write t equal to 0, and in that case t equal to 0, this function has the value equal to 0. Then the term that will be in the right hand side is I omega c, okay, then a1 minus a2, that is also written here. I omega c a1 minus a2, that is equal to 0, or a1 minus a2 is equal to 0, from here a1 is equal to a2, and also we obtained here a1 plus a2 is equal to 1 by root 2 pi minus a2 plus infinity fx to the I omega x dx. So from here you can write that solving equation, this is equation 5, and equation 7, that is equation 7, that f of omega 0, that is equal to a1 plus a2, again a1 minus a2, that is a1 is equal to a2, and from here you can easily calculate that a1 is equal to half of f omega 0 as well as a2 is equal to half of f omega 0. So therefore f omega t is equal to writing the value of this a1 and a2 in equation number 4. That is, this is equation number 4. F omega t, that is a1 and a2, we conversion a1 into this, a2 into this. So writing the value of a1, that is half f omega 0, that is here. That is here, half f omega 0. So half f omega 0 is the common term. Since a1 and a2 are equal, e to the power I omega t plus e to the power psi omega t, and this is it. This can be obtained from equation number 4. So taking inverse Fourier transform. Now taking the inverse Fourier transform of f omega t, that is nothing but yxt. That is equal to 1 by root 2 pi minus root plus infinity, then f of omega t e to the power minus I omega x d omega. Here d omega. So that is 1 by root 2 pi minus root plus infinity. Just substitute the value of f omega t. That is here half f omega 0. Then e to the power e to the power I omega ct plus e to the power minus I omega ct. Then e to the power minus I omega x and then d omega. So that is equal to 1 by root 2 pi minus root 2 plus infinity. Then half f of omega 0, you can write this e to the I omega ct minus x. Ct minus x. You can write this d omega. This is the first term. This term, and this term. Plus for the second term, this term, and this term. That is here 1 by root 2 pi minus root plus infinity half f of omega 0 e to the minus I omega ct plus x d omega. This is the solution for y in case of wave equation, one dimensional wave equation. Okay. Now another problem is here. The problem is here del u del t is equal to del 2u by del x square when x greater than 0, t greater than 0, subject to the conditions u equal to 0 when x is equal to 0, t greater than 0. That means when x is equal to 0, then u is equal to 0. And u is equal to 1 when 0 less than x less than 1, and 0 when x greater than is equal to 1. Obviously in this case t is equal to 0. And the third condition is uxt is bounded. That means del u del x tends to 0 as x tends to 0, and uxt tends to 0 for x tends to infinity. These are the conditions, and we will use this condition in solving this problem. So the differential equation that is given here, del u del t, that is del 2u by del x square. This is equation number 1. Now taking the Fourier transform on both sides of this equation, we have obviously in this case we have taken Fourier sine transform. So Fourier sine transform is square root 2 by pi 0 to infinity del u del t. This is the first term is here del u del t, then sine omega x dx. That is equal to root 2 by pi 0 to infinity. Then this term del 2u by del x square, then sine omega x dx. So that is from here root 2 square root 2 by pi. Then you can write this as del t 0 to infinity or ddt 0 to infinity u sine omega x dx. That is equal to root 2 by pi square root 2 by pi. Then you can write in this case, in this expression, in this integration, we are here to integrate this equation using the formula integration by parts. So for that case, taking sine omega is the constant. So sine omega x is here, and integration of del 2u by del x square is del u del x. The limit is 0 to limits are 0 to infinity. Then minus this 2 root square root 2 by pi. Then 0 to infinity, the limit integration sign and limits of integration is here. And now just differentiate this term, that is omega cos omega x, then integrate this term del u del x dx. So using integration by parts, we have these two terms from this. Okay, first in this case sin omega is taken as first constant, so this is first taken as constant, then integrate this term, so that will provide you this value, and after that minus sign is here, then 2 square root 2 by pi, then differentiate this term omega cos omega x, then integrate this term del u del x dx. Okay, now from here you see that in this case this 0 to infinity u sine omega x dx, the function, this is the Fourier sine transform of the function u, that is u s of omega. So this term 0 to infinity square root 2 by pi, then 0 to infinity u sine omega x dx. This is the Fourier sine transform of the function u, that is us of omega, and this del dt is here. That is equal to, you write here the limits, first infinity, So in case of x is infinity, in that case, your sine omega into infinity, that will give you 0 result, and for 0 it is also 0. So from this term is actually 0, gives you 0. Okay, and also not from that, also you can use this boundary condition. This boundary condition, you can also use this boundary condition. Del u del x tends to 0 as x tends to infinity. So here del u del x, for x is equal to infinity, this term del u del x is 0, and then for the lower limit 0, sine 0 will give you 0. So whatever be the value of this, for the higher limit, that is infinity, a del u del x gives you 0 result according to this condition, and when x is equal to 0, this sine omega x gives you 0. So actually this term is 0, that is 0, and then minus square root 2 by pi, this omega is taken here, 0 to infinity. After that, del u del x is here, cos omega x dx. Here the boundary condition is also given here. Okay. Now come to the point, that point, that is omega, okay, 0 to infinity del u del x cos omega x dx. Now that is equal to, you just write d, this is 2 square 2 by pi omega, and now you have to integrate this integration should be carried out using integration by parts, and in that case also cos omega x is taken first constant, then integration of del u del x, that will give you u, so minus 2 by pi square root of 2 by pi, then omega, then u cos omega x 0 to infinity is the limit, then minus this minus, and here another minus will provide you plus sign, then square root 2 by pi, this omega is here, then 0 to infinity, first differentiate this term, differentiation of this term will give you minus omega sine omega x, and integration of this term u, that is 0 dx. So that is equal to minus 2 by f square root 2 by pi omega, then u cos omega x 0 to infinity, then minus, this minus will appear here, minus square root 2 by pi, this omega omega square, 0 to infinity, u sine omega x dx. Okay. Now since uxt is bounded, this is another condition, boundary condition, that hence ux2 tends to 0 as x tends to infinity. So as x tends to infinity, then uxt tends to 0, and in that case the left hand side is here, d dt of us omega, that is equal to, from the first term when x is tends to infinity, so then u should be 0 according to this condition. So that will give, so this term will provide you 0 result when x is equal to infinity. But when x is equal to 0, then this u will provide you the value u0t, that is the u0t, and this cos omega x, that means cos 0, that will provide you 1. So this negative sign is here, and for the lower limit another negative sign will come here, so they will provide you positive sign. So root 2 square root 2 by pi, then omega, after that u0t into 1. Okay, from the first term you will have this. For the second case, you are here for the second case, you know that square root 2 by pi 0 to infinity u sine omega x dx, this is nothing but the Fourier sine transform of the function u, that is u is omega. Okay, do you understand? This minus sign is here, this omega square is here. After that, square root 2 by pi 0 to infinity u sine omega x dx. This is the Fourier sine transform of the function u, that is us omega. So we obtain this. Now writing this, transferring this term to the left hand side. So del d us omega dt plus omega square us omega, that is equal to square root 2 by pi, then omega u0t. Now from the condition number 1, go to the condition number 1. What was the condition number 1? When u is equal to 0, when x is equal to 0, t may have any value. So when x is equal to 0, u is 0. So in our present, in our present stage, that is in this stage, 2 by pi u omega u, in this case x is 0. So in the value of u 0 t is equal to 0 according to the boundary condition number 1. So this value d us omega dt plus omega square us omega, that is equal to 0. And from here you know how to solve this problem, and solving this you have us omega, that is equal to a e to the power minus omega square t. You know to solve this. You know the solve the equation du dx, the dx by dt plus omega square x is equal to 0. You can solve that problem. You know, in that case u of us omega should give you or provide you the solution as a e to the power minus omega square t, where a is an arbitrary constant. And the value of this arbitrary constant can be calculated by using imposing or using the boundary conditions. So finally we have obtained us omega, that is a e to the minus omega square t. This is equation number 2. Now when t is equal to 0, the Fourier sine transform of uxt is, so when t is equal to 0, so now first let us write the Fourier transform of uxt. So in this case u of s x omega t, that is equal to square root 2 by pi 0 to infinity u x t sine omega x dx. But when t equal to 0, then it will provide you us omega 0. Just concentrate here. If for the function uxt, the Fourier sine transfer gives you us omega t, that is equal to square root 2 by pi 0 to infinity u x t sine omega x dx. Now for t equal to 0, it will give you us omega 0, that is equal to square root 2 by pi 0 to infinity u x 0 sine omega x dx. Okay. Now this is equal to square root 2 by pi, and now we have to go to the boundary condition, that is ux 0. Where is that? That is here. See here, u is equal to 1, 0 less than x less than 1. This is the condition. From here you can easily obtain that using this condition. Use this condition. When 0 less than x less than 1, then u is equal to 1, otherwise it is 0. So now using that, so that using that we are here, that is here. So 0 to infinity means 0 to 1, we are taking 0 to 1, and in that case ux0 is 1, otherwise it is 0. So remaining terms should be nullified, and that cannot be accounted here. Only 0 to 1, this limit will be considered, and in this case in the limit 0 to 1, ux0 has the value 1, and then sine omega x dx. This is according to the definition of the function that is provided for the beginning or the problem, or within in the problem. So that is here. So now writing this, so 2 by square root 2 by pi is here, and integration of sine omega x is equal to cos omega x by omega with a negative sign, and the limits are 0 to 1. So us omega 0 from here, that is equal to this minus sign is here, square root 2 by pi, then for x is equal to 1 cos omega by omega, and then minus for 0 it is 1, so you can write minus 2 by pi square root 2 by pi cos omega minus 1 by omega, that is equal to, you can write 2 by pi square root 2 by pi 1 minus cos omega by omega. You can write also this. And now from equation 2, this is equation number 2. Now from equation number 2, if you use t is equal to 0 in this equation, then us omega 0, that is equal to, from here a 0, a, only from here e to the power 0 means a. So us omega 0, that is equal to a, and the value of us 0 from here also we have calculated, that is equal to square root 2 by pi 1 minus cos omega by omega. So the constant a has the value square root 2 by pi 1 minus cos omega by omega. Now substituting this value in the expression of us omega t. So us omega t means this is actually nothing but us omega t. Okay, so us omega t is equal to square root 2 by pi. The value of a is here, square root 2 by pi, then 1 minus cos omega by omega, then e to the minus omega square t. Just substitute the value of a, that is equal to this, in the expression in this expression. So finally, we get this us omega t, that is equal to square root 2 by pi 1 minus cos omega by omega e to the minus omega square t. So you have succeeded to find out the value of the Fourier transform of the function uxt. This is here, and once you have successfully calculated the Fourier transform of the function uxt, then you can easily find out the value of uxt by using inverse Fourier transform. So the inverse Fourier transform of this u is omega t, that is equal to u of xt. And since this is the Fourier sine transform, so you should also have to use the inverse Fourier sine transform. That means uxt, that is equal to square root 2 by pi 0 to infinity u is omega t, then sine omega x dx. That means u of xt, just use the value of, substitute the value of u s omega t, that is here. So root square root 2 by pi 0 to infinity, then square root 2 by pi, then 1 minus cos omega by omega, then e to the power minus omega square t, then sin omega x d omega. That is equal to this term, and this term will provide 2 by pi 0 to infinity 1 minus cos omega by omega e to the power minus omega square t, then sin omega x d omega. So this is the solution for u, that is uxt, and in this case we have succeeded, or we have successfully calculated the value of uxt in terms of the Fourier transform of this function. So now one thing you have to do, you have to practice all the calculations, and which will make the problems easier to use.